Hi, folks. I'm going to record just quick solutions to the quiz that was from this last weekend here. So I'm going to start it off with question one. So question one has to do with this function f of x equals square root of x. And for any calculus problem involving roots, the first thing we're going to do is just rewrite that as a fractional exponent, so x to the 1/2 power. This is a four-part question here. Part one actually doesn't even involve any calculus. It just asks us to evaluate f of 16. So f of 16 would be the square root of 16, or 16 to the 1/2, and that's just 4. Note it's not plus or minus 4. The square root function is a function. It only has a single output. So when we just write the square root, it's always going to output the positive answer. That's why in the quadratic formula, for example, we have to put a plus or minus if we want both the positive and negative results there. So this would be question 1, or 1.1. And then 1.2 asks us to evaluate f prime of 16. So first we'll need to find f prime of x. Since f of x is just powers of x, we can use the rule for that. So 1/2 comes out in front, and then the power will drop down by 1. 1/2 minus 1 is negative 1/2. Another way of writing this, don't feel like you have to do this, but especially if you look at problems online, you might see this written as 1/2 times the square root of x. These are the exact same expression. Remember, negative exponents just mean take the reciprocal. So take the reciprocal of square root x, multiply by 1/2, we get 1/2 root x. And so then f prime of 16 is 1/2 times 16 to the negative 1/2, or 1/2 times 1 over the square root of 16, or equivalently 1/8. Okay, so problem 1.3. Sorry, bear with me here. Okay, problem 1.3. Back here. Okay, so 1.3 asks us to write the equation for a tangent line. The tangent line is not at x equals 16, but at x equals 4. So we want the tangent at x equals 4. And for any problem involving a tangent line, really we need two things. We need the slope of the tangent line, which is given by the derivative. So we'll need f prime of 4. And then we'll also need a point on that line. So we'll evaluate f of 4. Well, f of 4 is just the square root of 4, so 2. And so that tells us that the point 4, 2 is on the curve. And f prime of 4, we can use our derivative earlier to find f prime of 4. Okay, well that's 1/2 times 1 over the square root of 4. 1 over the square root of 4 is 1/2. And so what we're looking for here is a line with slope 1/4 and going through the point 4, 2. So the easiest way to do that is point slope form, y minus 2 equals 1/4 times x minus 2. And don't feel like you need to do anything else. This answer is perfectly good the way it is. So just quick recap there. I evaluated f prime of 4. Right, that's going to give me the slope of the tangent line at the point where x equals 4. And then I plugged in 4 to the original equation to get the y value. So now I have a point, and I have a slope, and I use point slope form to find the equation for the line. Okay, finally, part 1.4 here. You're asked to use differentials and your results above to estimate the square root of 15. I'm going to do a little diagram here just to make sure that we all understand this question in the same way. So what we have here is we have a square root function. It looks something like this. And there are certain known points. So for example, when x equals 16, we know what the square root of 16 is. We know that it's 4. And so now the square root of 15 is whatever the height of this point is right here. It's going to be a little bit less than 4. And our strategy here, if we're going to use differentials, is to find a tangent line and follow that tangent line 1 unit to the left. So let me just draw that a little bit larger here. So it's a blown up version of what we're seeing there. So we have our curve. We have a point here, right? That's the point at 16, 4. Then we have a tangent line, and we're going to follow that tangent line back 1 unit. And this point here is going to be a pretty good approximation of the actual square root of 15. There's x equals 15. Here's x equals 16. We don't know what x equals what the square root of 15 is. It's an irrational number, but we could follow this tangent line back by 1 unit. Okay, so let's see what's the differential form here. each one of these problems involving differentials, what we can do is we can just start with y prime equals dy dx, or really f prime of x. So f prime of x equals dy over dx, where dy and dx are small changes in x and y. If we rewrite this in our differential form, we get dy equals f prime of x times dx. That is, a small change in y will result from multiplying the slope of the tangent line times a small change in x. Well, in this case, our change in x would be how much we change x by to go from 16 to 15. So dx would be minus 1. We know what f prime of x is. F prime of 16 we've done earlier in the problem here. F prime of x is 1/8. And so what that tells us is the change in y going from our known point here on the curve to our unknown point that's an estimation of the curve. The change in y will be 1/8 times the change in x. So negative 1/8. Or in other words, our estimate of the square root of 15 will be 1/8 less than our known value for the square root of 16. And so then our conclusion is square root of 15 will be approximately 4 minus 1/8. And we could write that in one of two ways, either 31 over 8, right? So 32/8 would be 4. Or as a decimal, I think it's at 3.875. Either one of those is good. Okay, guys, so on to problem 3. Problem 2 just asked you to upload your work. Please make sure you do that. One, it's a check on academic integrity. If you've done problems involving derivatives, you had to write down something somewhere. You can get a maximum of half credit if you're just submitting answers without some sort of documentation. If you don't have access to a camera, please try and find one, or at least type up your steps in Microsoft Word. It's a bummer to see people who have right answers but haven't uploaded any work. So anyway, enough on that. Let's go on to problem 3. Problem 3 involves some real-world data about new COVID cases in Montana here. And so I gave you this data. This is real data, by the way, or at least the best data that I could find. On a weekly basis, once a week, how many new daily cases were there on these 4 dates? And this is an interpretive question more than it's a calculation question. There are a few basic calculations involved. But my hope, a year from now, is that you'll be able to answer questions like this, even if you don't remember the quotient rule, that you'll be able to think in terms of rates of change. And that's what this question is really about, is understanding how we can use functions to model rates of change and how different derivatives might be related. Okay, so question 3.1 asks you, in which of the 3 weeks was the average rate of change in new cases the greatest? Okay, so here we can only really calculate average rate of change from date to date here. So going from 37 to 67, that represents a change of plus 30, right? That would be the change in C. Luckily, these dates all are at 7-day intervals. We could still calculate average rates of change for different interval lengths. That would just make the problem a little bit more challenging. So our average rate of change here would be 30 cases over 7 days, right? So that's the change in new cases over the change in time. So that's a little bit more than 4. We could say it's I don't know, maybe 4.1 or 4.2. And what that would mean, just to interpret this meaning here, is in that first week, each day there were 4.1 more new cases than there were the previous day, on average, right? That's an average rate of change. It might have changed day to day. In fact, if you start looking at this data on a daily basis, it gets really interesting because hospitals don't necessarily report these things 7 days a week. So you'll often see on Mondays, there's a significant uptick, and there aren't very many reported new cases on Sunday or Tuesday, for example, compared to that. So it's not bad to take a weekly snapshot or a 7-day running trail. Okay, so there's our average rate of change. We don't actually need to calculate each one of these because for each one of these time intervals, the change in time is going to be 7 days. We can just look at by how much the cases changed here. So let's see, 95 minus 67, I believe that's 28 new cases. And then in this last period here, we have plus 40. Okay, so clearly the most change in cases was over the week from July 8th to the 15th. If we needed to calculate that as a rate of change, a couple students did. It would be 40 over 7. I don't know what that is as a decimal. But again, that represents the average rate of change between one daily rate and the next daily new cases. Okay, so let's see, part 2. In the context of the problem, explain what C prime of t, the derivative with respect to time of C of t, represents. Well, we've sort of alluded to that already in calculating these average rates of change. And I want to give a couple examples of answers that were close but not correct. So for example, C prime of t does not tell you how fast the number of cases is increasing. If you think about it, there's a whole bunch of people in the hundreds or perhaps thousands in the state, I don't know where we're at right now, of active cases. The new cases are the change in the active cases, or they're part of the change in the active cases. So the C of t is already a rate of change related to how many people are infected. So C prime of t is a rate of change of that rate of change. So I think maybe the best answer that you could give here is C prime of t gives the instantaneous rate of change of new daily cases of COVID-19 in Montana. There are some folks who are like, close to that. One way to be sure that you don't get full credit is to say something like, well, C prime of t is the derivative of C. You just sort of state the definition, but you don't explain what it means. Anytime you're given a problem that asks you to explain in the context of the problem what it means, you should be talking about, infected people and days. And if you don't do that in your answer, it's not a full explanation. Think as if you're explaining this to someone who hasn't taken calculus. Say, okay, I got this C prime of t, and they want to know, well, what does it tell me? And you have to explain it without just referring back to a calculus definition. So again, C prime of t is the instantaneous rate of change of daily new cases in Montana COVID-19 cases. Okay, so on to 3.3. C of t is in fact a rate of change, true, and it can be thought of as the derivative of some other function. Okay, that's getting a little bit complicated. So we have C, we have the derivative of C, C prime, and now we're saying there's some other function for whom C is the derivative. So we're calling that function P of t, and so that sets up this relationship here. We're on the 3.3 here. So we have C of t, we have P of t. So P of t, the derivative of P is C, right? So P prime of t is C. And then C prime of t is what we just talked about in the previous problem here. So we have 3 levels of derivatives. We have P of t, we have C, and we have C prime. So what does P of t represent? Again, the parts of this question connect. So if C of t, we've already been given that that's how many new cases there are. The question is really asking, well, what is that a rate of change in? Well, it's a rate of change in the total number of people who have caught COVID-19. It's not exactly a rate of change of the number of active cases. The number of active cases would actually have 2 different derivatives that would play into it. So we'd have we'd be adding to that total via C of t, the new infections, and we'd be subtracting from that total anyone who's recovered, or unfortunately anyone who's passed away. So there are a few people who said that. They said, okay, well, P of t is the total number of active cases. And I think I give full credit with a little note, even though it's not quite right. The best answer would be P of t represents the total number of cases, not active cases, just the total number of people who have caught COVID-19 who are residents of Montana. So there's the best answer there. I had a few people who I think were maybe misled by the fact that the variable was P. Maybe you associated this with another problem you've done in the past where P might represent population. Just because it's the letter P doesn't really lead us in any direction as to what its meaning could be. So don't read into it in that direction. Really, the key relationship here is that the derivative of P is C, and that should be enough to unlock this problem here. Okay, so one more part. We have part 3.4. Sorry, my copy here is behaving a little bit weird. Okay, so 3.4. Suppose you're a public interest data journalist reporting on the spread of COVID-19 this summer. How would you report on the following? And there's 2 pieces of data here. The first is that C of 197 equals 136. Okay, so that's just our function C. That tells us that there were 136 new cases on day number 197, which is July 15th. So that part hopefully is pretty easy. You can say something along the lines of, on that day of July, there are 136 new cases. And then the second part's interesting. Second part is C prime. So C prime, the derivative of C on that same date, is greater than 0. And this should have been the conclusion that we had based on everything else that we've done in the problem here. Not only is the rate of change positive, but it's increasing, right? So the number of new cases is positive, so we're adding to the caseload, and the number of cases per day is increasing. Another way to say that is that the total number of cases is accelerating in Montana. There's some good news in Gallatin County, at least just the last couple of days. We're now almost a week since this data was fresh. The Gallatin County cases, the new cases are starting to decline, or at least they've declined over the past couple of days, hoping it will stay that way. Okay, so problem 4 asks you to sketch a graph. And I've spoken with a couple students about problems like this. For some people, they're the most challenging problems out there. And I would tend to agree. What makes them challenging to both teach and learn is that they're not procedural in the same way that taking derivatives or limits is. It's not like, oh, well, we always do this and we always do that. What we're doing is we're taking from a group of clues whatever information we can to create a product that meets these criteria. So there's 5 criteria. I just wrote them on the whiteboard here. We can sort of go over them one by one, and then I'll start drawing. So continuous on the open interval from -5 to 5. So that just means I can draw it without picking my pencil up off the board, or my marker off the board between -5 and 5. It could be discontinuous outside of that. F of 1 equals F of 4 equals 0. Okay, so what that means is that when x equals -1, y equals 0, and when x equals 4, y equals 0. So you know what, I might actually just use that piece right now, because that actually gives me some information about what this graph must look like. And I apologize, I don't have all the colors of markers here. It might make it a little bit easier. I think we'll be able to get by with just purple here. Okay, so what I just said is when x equals -1, y equals 0, and when x equals 4, y equals 0. So those 2 points are definitely on the graph. I have a local maximum at -2, 4. Okay, that I can also put into my graph. So -2, 4. Again, that's a point that's actually on the graph there. An inflection point at 0, -1. Okay, so there's another point on my graph. There's 0, -1. And then f of 2 equals -3. Okay, one more point, so f of 2. So when x equals 2, y equals -3. And then we have a couple other things that we haven't really used yet. Okay, so let's see what we have so far. So all I really have to do here is some like fancy version of connect the dots. There's a few interesting points here, and I didn't copy this down fully, but it actually says that this inflection point is the only inflection point. And what that means is the function has to maintain the same concavity on one side, like concavity in one way, concavity another way over here. And it can't switch anymore. And I haven't really done a great job of drawing this to scale here, so I might need to readjust my axes a little bit to accomplish that. In particular, I think this minimum is going to have to be a little bit lower just to maintain the scale over here. So there we go, something more like that. And we'll see if we can make that work. Okay, so let's see what we have here. I'm going to start actually with this last piece. This is an interesting one. So what I've given you is the function value, so 2, -3. I've told you that the derivative evaluated at that point is 0, so that means there's a horizontal tangent here. And then f double prime of 2 is 1. Well, what does the second derivative tell us? It tells us concavity. So we have a concave up function with a horizontal tangent. That means that this must be a local minimum. You could read this entire line as just saying there's a local min at x equals 2 and then y equals -3, right? That would be how to interpret that last line there. So, okay, so I can start to draw that in. I can start like drawing it as if it were minimum. And so what that means is at this point here, at the inflection point, it must be concave down prior to that. And that's where, like, again, I just need to like do a better job of drawing scale here. Like that, a little bit easier to draw. Okay, so I now have a local maximum here. I have a local minimum there. It's continuous. I need to hit these zeros. So maybe something like this. And my graph is not great right now. I don't know. I would probably, if this were a student response, I'd have a note saying, okay, it looks a little funky in here. Again, it is possible to draw this graph. Should be able to draw this graph the way it was written, or at least very close to it. I want to point out one really common mistake that I saw, and it has to do with this inflection point. A lot of people looked like they had a graph like this, and then they like changed it so it was like something weird like that, or like this. An inflection point doesn't need to be that crazy looking. Like somewhere in between this graph here is like somewhere in here is an inflection point where it switches between concave down and concave up. Oftentimes, you know, it will look very linear at that point. It doesn't need to be exaggerated and curvy. I gave some feedback on that, but I didn't deduct a whole bunch of points if that was the only error. Okay, so question 5 has a graph that looks something like this. Again, apologies for the quick sketch, but this will do to just show what we need to do here. So this is the graph of y equals g of x, and you're asked to draw y equals g prime of x. This is a problem that's probably easier in person than online. It's easier to draw the graph of g prime directly on the same graph here, because we can do things like this. I can identify places where the graph flattens out and has horizontal tangents, like right here. Okay, so if there's a horizontal tangent, then the graph of the derivative must equal 0 at that point. Likewise, I have a horizontal tangent here, and so the graph of the derivative must be 0 there. And again, over here, the tangent line would be horizontal, and so I have a point there where y equals 0 on the graph of my derivative. So now I have 3 points that are on the graph of the derivative. And to fill in the rest, I'm just going to observe a couple things. First, this is a smooth curve, and so its derivative should also be smooth. It's continuous, and no holes or gaps or anything like that. In between the local minimum and the local maximum here, the graph that I was given increases, right? It increases gradually and then faster and then gradually again. And so the graph of my derivative should be positive, not too positive. It's not too steep of a tangent line in between here. So it starts at 0, increases, and then it's back to 0. And then it decreases gradually and then flattens out again. So something like this, right? My derivative is negative, precisely where the original function is decreasing. And then to the right, it increases, right? The original function increases, and so my derivative should be positive. Not just positive, but probably positive and getting steeper. So something like this. And then finally, the first interval here coming up to my local minimum, the function is decreasing, in fact, decreasing rapidly and then flattening out. So that would correspond to a negative derivative that then gets closer to 0 just as the function flattens. Okay, so here's a possible graph. As long as you had these 3 zeros that were aligned with the local extreme of the original graph and they're connected in a smooth fashion, you likely got full credit on this problem. Okay, here's problem 6. You're given 2 pieces of information, which is nice. You didn't actually have to find any derivatives for this problem, but you did have to work with them. So first, for some function f prime of x is given by 4 minus 4x squared over x squared plus 1 to the 2nd power. And then f double prime of x is 8x times the quantity x squared minus 3 over x squared plus 1 squared. You don't have to check these things to make sure that they are actually derivatives of each other, but we do have to be able to work with them. And we've been asked a variety of things on this problem. First, about an interval of increasing behavior. Second, about an interval of concave downwards behavior. And then about coordinates of any local maxima or minima. There's a 4th question that we'll get to in a minute, but all 3 of those the first 3 questions really have to do with whether f prime is positive or negative, whether f double prime is positive or negative, and where f prime might actually equal 0. So what I'm going to do to start this problem is actually factor each one of these f prime and f double prime. I want you to observe something about the denominator of each one of these fractions. We know that when we square any real number, we get a non-negative number. The smallest that x squared could ever be is 0. If we take something that's at least 0 and add 1 to it, then we always have something that's at least 1. If we have something that's at least 1 and we square it, we will always have something that's at least 1. what I'm saying here is that this denominator will never be 0 and will never be negative. And so really what we can do, I'm going to cross it out. It's not canceled, but we can ignore it. It's never going to make the derivative undefined. It's never going to change the sign of the derivative. So what we can do is really focus in on the numerator there. And same thing down here. Again, I'm not canceling. It's not going away. But we know that x squared plus 1, the quantity squared, can never be 0 and can never be negative. And so what's going to determine whether these derivatives are 0, positive, negative is solely the numerator here. Okay, so the numerator here can be factored. I can do that in 2 steps. First, I hope you can see I can factor out a 4. And that would leave me with 1 minus x squared. And 1 minus x squared is just the difference of 2 squares. So 1 plus x and 1 minus x. Okay, and I should, just to be mathematically correct, I'm still going to have the same denominator here. So x squared plus 1, the quantity squared. But we know that's not really going to do anything for the problem. Well, this is good, right? This now tells me 2 different points. There'll be critical values, making the first derivative 0. So x equals -1 and x equals +1. Those will be critical values. Those will divide the real number line into intervals of increasing and decreasing behavior, perhaps. They may also be local maxima or local minima. All right, so just in the same vein here, I'm going to try and factor. I already have it partially factored. I definitely don't want to distribute that 8x. It's already partially factored. And I can also factor this more. Again, x squared minus 3 is the difference of 2 squares. It's not as obvious as when one of the squares is like 16 or 1, but 3 is a perfect square. 3 is precisely x plus root 3. X minus root 3 will give us our x squared minus 3. And then again, this same guy down here, so x squared plus 1 to the 2nd power. Okay, so I've factored f prime and I've factored f double prime. And I'm going to start by making that number line for f prime, or sorry, that sign chart, I guess. It is the real number line. And I'll put values of x up here, and I'll put values of f prime of x right here. And my 2 critical values then come from setting this equal to 0. So our critical values are x equals 1 and x equals -1. So here's x equals -1. Here's x equals 1. And to determine the behavior here, I actually want to show you a little trick here that will help us with f prime. Since we have it in its factored form, we can look at what happens to the factor 1 plus x and look what happens to the factor 1 minus x. And then simply multiply the signs of those 2 things together. So I'll show you what I mean. If x is less than -1, well then the factor 1 plus x will also be negative, right? Because we're adding something less than -1 to +1. If x is greater than -1, if it's like 0 or something, well then we get a positive result. And if x is greater than 1, we still get a positive result when we add it to 1. So this is a sign table just for the factor 1 plus x. For the factor 1 minus x, if I take 1 and I subtract -1 or smaller, I get a positive number, right? Because subtracting a negative number is the same as adding. Likewise, if I take a number in between -1 and 1, so 0, for example, I still get a positive number when I plug it in for x in this factor. It's only when I have a value of x that's greater than 1 does the factor 1 minus x become negative. Okay, well now what we can see is that f prime of x is just going to follow the signs of these 2 things, right? And we know that like a negative times a positive, right? So if f prime is made up of a negative times a positive times this other stuff that doesn't change, well then f prime will be negative, and then f prime will be positive, because a positive times a positive is positive, and then f prime will be negative again. And so that establishes 3 intervals, 2 intervals for decreasing behavior, so x less than -1 and x greater than 1, and then 1 interval for increasing behavior that occurs in between x equals -1 and x equals 1. So we now know that we have increasing behavior on the interval -1 to 1. Now I'm going to see if I can fit my, my second sign table here, and I'm going to actually align it with my first one, because we can use this information together now. So I'm going to make a sign table for f double prime. I'm going to do it in the same way that I did this last one. I'm going to do it by factors. So let's see, I have a factor of 8x. I have a factor of x plus root 3. And I have a factor of x minus root 3. And so this is going to give me 3 different signs. The sign table is going to be divided by these 3 values here that make it 0. So x equals 0, for example. That's a potential inflection point, right? That would make this factor in f double prime 0. X equals negative root 3, and I don't know exactly where negative root 3 is, but I know it's farther away than negative 1. And then positive root 3. Positive root 3 is more than 1, so I'll put that there. And then we'll try and figure out the sign of each one of these things here. Maybe I'll start with 0, because that's easy. Okay, so if x equals 0, then 8x is 0, right? So we know that the second derivative itself will be 0 here. And then that's the dividing point. Everything to the right will be positive for the factor 8x, and everything to the left will be negative, right? All we're doing is taking that number, multiplying it by 8. Okay, how about x plus root 3? Well, obviously, if we start with a positive number and we add root 3, we end up with a positive number. If we started with a number that's negative but greater than negative root 3, we'd still end up with a positive number and we add root 3 to it. And if we start with a number less than negative root 3, we'd have a negative number. Slide this over a little bit. There we go. Minus and minus. Okay, last factor here, x minus root 3. Okay, so we're going to subtract root 3. Well, obviously, if we start with a negative number that's less than negative 3 and we then subtract root 3, it'll still be negative. Same thing here. If x is in between 0 and root 3 and then we subtract root 3, we'll get a negative result. And then finally, if it's big enough, it will stay positive. Okay, so now this sets up a sign table for f double prime. This should be clear that that's what we have down here. This is a sign table for f double prime. So negative times a negative times a negative is negative. Okay, so I'll just summarize that. 2 negatives times a positive is positive. 2 positive times a negative is negative. And then all 3 positives multiplied together is positive. And so what that tells us is our function is concave down when x is less than negative root 3, concave up in between negative root 3 and 0, concave down between 0 and root 3, and then finally concave up for x is greater than root 3 here. Okay, so 2 different intervals of concavity for concave down. I'll summarize those over here. So concave down, we have from negative root 3 to 0, and then either comma or a union. We also have from, oh, sorry, I have that backwards, right? So it starts, yep, I have that backwards. So we actually want negative infinity to negative root 3, and then from 0 to root 3. Those are 2 intervals, so here and here. Okay, now here's the cool part. The work that we've done for 6.1 and 6.2 can actually finish the local maxima minima question for us without any extra work. And it's because we've made these sign tables and also because I've kept them kind of lined up. So what we know, if we're looking for max or min, we need 2 things to be true. We need, for local max, the derivative should be 0 or undefined, but 0 in this case. And then we would need the function to be concave down. Well, we have 2 points where we know that the function is has a horizontal tangent line. And then the question is, are there any maxima or minima here? Okay, well, at -1, let's see what's happening. So at -1, we have a horizontal tangent. And just looking down at the concavity, we have positive concavity in between negative root 3 and 0. So that means up, concave up. So we'd have something like this. And then at x equals 1, we have a horizontal tangent, and our function is concave down. So something like that. And so I believe, I think I gave, if you found either one of these points, I think I gave full credit on this, just because it was hard. There wasn't a lot of room to give a full answer here. The other tricky things, we don't actually know the y values. But we do know a maximum occurs when the function is concave down, so at 1 comma f of 1, and a minimum at -1 comma f of -1. Oops, not -1. So that would be probably the best answer you could give. Again, if you found either one of these and indicated it, I think I gave you full credit on the question. Okay, so finally 6.4 asks about the end behavior of this function here. And the fact that it's f prime of x doesn't matter at all. We're just finding the end behavior of this function, not f of x. So to find the end behavior of a function, we just take the limit as x approaches infinity or x approaches negative infinity. And there's a test here. What we can do when we have a rational function like this is just look at the degree of the numerator and the degree of the denominator. If the degree of the denominator is greater than the degree of the numerator, then we'll have a horizontal asymptote at x equals 0. And without even doing much algebra, we can imagine what happens when we square out this denominator. We're going to get x to the fourth plus a whole bunch of other stuff that I don't really care about, right? The important thing is what's the highest power of x. We take x squareds and we multiply them by themselves, right? Using FOIL here, we will get x to x to the fourth. The other stuff doesn't really matter because all we care about is the highest degree of x that we find here. So we have degree 4 in the denominator, degree 2 in the numerator. That means that the denominator wins, right? And it draws the graph down to 0. So we're going to see a horizontal asymptote at x equals 0. Y equals 0. So you can answer this a couple ways. Horizontal asymptote, y equals 0, or approaches the x-axis, something like that. And the problem's done. If they had the same degree, it would be a little bit trickier. We'd have to use some other techniques, but hopefully this one was not so bad. Okay, so question 7 asked you to just upload your work from the previous problem. So hopefully you did that. And then question 8, unfortunately, I omitted a domain for that. I do want to still briefly talk about question 8, because you could have a question like this on the exam. Well, if they ask you for absolute maxima or minima, that means the highest and lowest y values on the entire domain. And we find that by doing two things. First, by identifying any relative extrema, so just hilltops and valleys. And then finally, by evaluating the function at the endpoints of that interval. Without the endpoints of the interval, we can't really say what the highest and lowest points are. And so it's important to do that for a problem like this. That's why you couldn't do this particular one. So the steps for absolute extrema, find any relative extrema, and then compare those to the y values at the endpoints of the interval. Whichever is the highest y value is the absolute maximum, whichever one's the lowest is the absolute minimum on that interval.